Some operate on short, independent clips, which limit their ability to reason over long-term context. Others instead process the entire video offline, which impairs their applicability in streaming-like scenarios. So in this work, we aim at retaining the benefits of both the approaches. In particular, what we observe is that the Segment Anything 2 already introduced a memory bank that retains information from past frames, allowing for context-aware streaming segmentation. So this brings us to the central question: can we transfer the tracking and segmentation capabilities of Segment Anything 2 to perform streaming referring video object segmentation? So this seems like a natural next step. However, there are some not trivial challenges. First, text understanding. Segment Anything 2 supports only geometric prompts like points or boxes and has no native support for semantic prompts like language. Second is temporal modeling. So in Airbus, it's not enough to match visual appearances across frames, as we also need to recognize objects based on how they act over time. So this means that we need to model their temporal evolution, but Segment Anything 2 process frame independently. And third, we identify an issue that we denote as tracking bias. When the target object is occluded, ambiguous, or not yet visible, Segment Anything 2 start tracking an object that only partially matches the text. So without a human correction, such error can persist across frames, even when a new object more aligned with the prompt appears in the video. So in this work, we address these limitations and we make SAM2 wiser. So we enable text understanding, temporal modeling, and the ability of correcting tracking mistakes, all without any fine-tuning and without relying on external large visual language models. This is the architecture of SAMWISE. It builds entirely on top of a frozen Segment Anything 2 and a frozen text encoder. We add and train only few lightweight dedicated modules. To enable text understanding, we start by selecting the contextual token from the referring expression. This contextual token represents a whole summary of the referred object. We then expand the prompt encoder of Segment Anything 2 with a learnable projection that maps this token into the prompt space. In this way, we let the token directly guide the segmentation process. To unify visual and textual modalities, we introduce a novel cross-modal temporal adapter inserted at multiple layers of the feature extraction stage and added in a residual fashion. These modules enables a deep interaction between the two modalities. In particular, what we do is to perform a cross-attention in both the direction to let each modality progressively enrich the other. In SAMWISE, we model the temporal modeling directly inside the feature space, inside the cross-modal temporal adapter. Our key insight is that motion modeling typically spans only a localized region of the image. So instead of attending globally, we perform a localized self-attention across spatially and temporally nearby regions of the image. In this way, we are able to model temporal evolution while reducing unnecessary computation. And finally, we address the problem of the tracking bias. So the phenomenon where SAM2 may start tracking an object that partially matches the text and persists in following that object even if a new one more relevant appears in the video. What we do is to derive a memoryless token computed as a cross-attention between the current frame features and the textual prompt. This memoryless token represents what the object should look like now, without being influenced by past prediction. So we compare this token with SAM2 mask token, and if the two differs, our conditional memory encoder encodes both the object representation into the memory encoder. In this way, we let Segment Anything 2 to balance historical context with unbiased current information. So let's look at a practical example that highlights the challenges of streaming referring segmentation. Here we have a short clip from The Lord of the Rings with a textual query that is the guy who is drinking. So at the beginning is not clearly identifiable who is the correct object, as none of the two persons is actually drinking. So SAMWISE start tracking one of the two persons, the ones that hold a glass more visibly. However, there is a certain point in the video where actually the other person starts drinking, so we are able to identify the correct object. SAMWISE detects this change and switches to the correct person, and as the motion unfolds, it keeps tracking that person even through occlusions and is able to recover that object after occlusion thanks to the memory bank mechanism. Numerically, our learnable projection unlocks the task of referring segmentation for segment anything, and adding our cross-modal temporal adapter and our conditional memory encoder further improve the performance of 10 points on the most challenging dataset that is MAVIS in referring video pre-segmentation, highlighting the contribution of each of our parts. SAMWISE is state-of-the-art across all the referring video object segmentation benchmarks, even when compared with the methods with billions of parameters based on large visual language models. SAMWISE delivers state-of-the-art performance also at image level. And finally, we add and train less than 5 million parameters, totaling 202, and making SAMWISE the smallest model in its category. So to conclude, SAMWISE consistently outperform all the previous methods, both at image and video level. And it does that by remaining the smallest model available. But what I think that is more interesting is that obviously we are not the first that try to augment segment anything with language. But what is different from all the previous methods is that we decide to not delegate the visual text alignment problem to an external VLM and then use segment anything just for the segmentation part. But we decided to align directly the segment anything representation with the textual embeddings. In this way, we have been able to not fine-tune any of the segment anything to weights, so preserving all its state-of-the-art performance on the promptable segmentation tasks, and without disrupting its streaming capabilities. So having a model that is still working online and is able to perform not only referring segmentation, but also promptable segmentation. So that's it. Thank you.
Finder. Let me, this one? No, just you can go to the Finder here. This slide should be more. Oh, okay, sure. More, and could you hide the banner?
Sorry. Hello everyone, this is Wenbo from Tencent Arc Lab. Today I'm going to share with you our DepthCrafter. It can generate consistent and long depth sequence for open world videos. Here are two examples. Depth estimation is a long-standing but fundamental problem. It predicts depth values that is the distance to the image plane from the RGB values. It serves as a bridge linking the 2D observations and the 3D real world. There are three major challenges in open world video depth estimation. The first one is how to generalize to open world videos, rather than being restricted to a specific domain. And the second one is how to achieve accurate and consistent depth prediction. The last one is how to deal with long videos, as the length of real-world videos can be arbitrary. To address these three challenges, we propose to leverage a video diffusion model for zero-shot generalization. This is because the pre-trained video diffusion model has been trained on various and a huge amount of videos. And we constructed a large-scale video depth dataset using the video stereo matching. To fully leverage our dataset and synthetic datasets, we designed a three-stage training strategy. We also tailored an inference strategy for extremely long videos using a segment-wise processing and stitching manner. Finally, our DepthCrafter can infer up to 110 frames in a single pass, and arbitrary lengths with our tailored inference strategy. Our DepthCrafter achieves total performance across all video depth benchmarks, like the Stentile, Skynet, Kitty, and Bone, while performing comparably in image benchmarks like NYU V2. Here are some visual examples in outdoor scenarios. Our method delivers significantly sharper and more stable results. The same observation can be seen in the indoor sense. In the wild videos, our method also produces more stable results than image-based approaches such as depth sensing V2 and Depth Pro. Here are more results featuring various things such as characters, scenery, sports, anime, games, and so on. Besides the quality, our DepthCrafter supports variable video lengths from single images to extremely long videos. This is an example from the Minecraft game. It is more than 1 minute, so I only show part of the video results. Our method enables various applications, including converting 2D videos to 3D duplicate ones. Here is an example showing the converted spatial video on the Apple Vision Pro. And it also enables video editing and some visual effects, such as adding fog, matching, and depth-based generation. We have open sourced the code and model, which have attracted strong community engagement. Our GitHub code has earned over 1.3 thousand stars, while our Hugging Face model have been downloaded more than 1.5 million. Additionally, the demo videos on the social media platforms have gained significant popularity. Beyond the depths, we also explored estimating point clouds from videos, such that we can reconstruct the full 4D sense. Also, our normal crafter can infer surface normal from the video with stable and crisp details. Here is a QR code for our project page. Thank you for your attention.
Thank you, Claudia, for the workshop, and we have got some Q&A. So please feel free to ask any question for the speakers. Yep. Sure.
This is for the first speaker. What's your loss function when you are adding the text and keeping the other two modalities stopping or closing? What's your loss function? How do you train?
Yes, we use standard entity and loss. So it is a traditional end-to-end training we send. So at the end, we obtain for the segmentation tool producing output some logic that has traditional spatial dimensions and a single channel in output. And so we compare that with in a supervised way on our label video data.
So it's a supervised.
Yes, it's supervised.
Like man drinking has been supervised.
Yes.
Okay. And how do you capture that temporarily? You have to be consistent across the plane, which is the second challenge. That's my last one.
Yes. So theoretically can